Okay, we're going to get started with the industry sessions. I'm Pat Hindle from Microwave Journal. We have 3 talks today. We have they're also our sponsors, so I want to thank them, Rohde and Schwarz, Analog Devices, and Qorvo. The first talk will be by Rohde and Schwarz, Towards a Quantum Advantage in Radar, and it's presented by Fabian Kronowetter. He's the Junior Development Engineer of Technology. Come on up.
Good, thank you very much, Pat, for the kind introduction. I'm happy to be here today. I hope you all had a nice lunch break. My name is already just announced. It's Fabian Kronowetter, and I'm working in the field of quantum communication and sensing with Rohde and Schwarz. And I would like to use the next 15 to roughly 20 minutes to give a short insight into the field of quantum radar, its promises, limitations, and also some fundamental physics behind it. In this project, we are closely collaborating with the German Aerospace Center, the Technical University of Munich, and also the Walter Meissner Institute. Good, let's get started. What is a quantum radar in principle? Well, I guess all of you know the basic idea behind a conventional radar, which is a detection scheme using electromagnetic waves at very specific frequencies to determine now a distance, an angle, or a velocity of objects. And such a scheme now typically consists of some transmitter generating microwaves, then some transmitting antenna, some receiving antenna, where of course a single antenna might also fulfill both purposes, and then some receiver and processor of the signal. Here on the slide on the right, you can see a schematic of the fundamental building blocks of a quantum radar. Similar to the classical counterpart, we have a signal generator, some transmitter and receiver antenna, and some receiver and processor. Important is now that in our signal generation, what we do is we generate so-called entangled microwaves. I will get back to that a bit later. Important is just that we generate 2 spatially independent modes from which we send one part out towards an object. This one we call the signal mode, by preserving the second part in our sending station, wherever that may be. This one is called the idler. The idea itself behind the quantum radar is quite simple. Signal and idler, if we generate them correctly, exhibit strong quantum correlations. And these we want to use in the detection in order to increase the signal-to-noise ratio of our scheme. To make use now of these quantum correlations, signal and idler need to interact physically in a very specific manner before they are measured. This now directly implies that the idler mode needs to be stored or delayed for the round-trip time of the signal mode, here illustrated by number 2, the quantum memory. In the detector itself, a quite specific circuit is required, which now lets signal and idler interfere, and which afterwards turns the remaining correlations into some measurable quantity. What would be now potential applications for this technology? If you look at space applications and, broadly speaking, tasks encompassing detecting and resolving space assets, or also ground assets, as we've seen in the morning session, and enhanced performance in general would be, of course, more than welcome. The content you can see on this slide was kindly provided by the project partners from the German Aerospace Center. For example, enhanced radar performance could improve maximal ranging distances and the accessibility of certain space orbits, as illustrated on the top right. Plus, very generally speaking, high-resolution images, either of space units or ground units, to identify damage, location, malfunction, or also some physical attack could be of interest here. As an example, at the center image on the bottom, you see a radar image of the International Space Station acquired by the IOSA system, so the imaging of satellites in space from the German Aerospace Center, with a total image size of 170 times 100 meters and a resolution of 5 centimeters. You can quite nicely see the characteristic features of the space station. And then on the right, you can see, for example, a damage to a Sentinel-1 satellite, so to the solar panel of the device, which was caused by an impact of some space debris. Thus, the idea of a quantum radar in principle enhancing resolution and or range for, but not limited to, space applications would be quite a wonderful idea. The question is now, is it straightforward to implement this technology, or how do we approach this? And the answer to that is quite simple. It's a no. The concept of quantum domination came up more or less 15 years ago now, and has had quite some ups and downs ever since. In the beginning, it seemed quite promising and lead people hope for some universal tool to improve radar performance and also to make some non-detectable objects, keyword jets, visible. But this soon turned out to be restricted to very specific working conditions. And then furthermore, the technological complexity of implementing such a scheme is really tremendous compared to classical radar. The whole journey of the radar is nicely reflected in the Science article behind the first headline displayed here. Generally speaking, it's quite controversial what has been reported about quantum radar, which also becomes apparent when looking at the second headline, which reads, "Quantum radars can detect the stealth jets as they use subatomic particles instead of the radio waves." This is straightforward nonsense. My goal is now to give you a better picture in terms of what can be really expected of this approach in principle and what is also achievable with currently available technology. Let us talk about the quantum advantage. What is promised? Well, theory now predicts an elevation of the signal-to-noise ratio of 6 dB, or a factor 4 in linear units. This is, to make it short, what can be expected, but as I already said, very specific parameters are required for that advantage. I picked out now the central, let's call it challenges of the scheme. If we start at the top left, an advantage in principle is only achievable for a combination of a strong background signal combined with a weak radar signal. This basic requirement now makes radar frequencies a natural choice due to the relatively strong thermal background at ambient conditions compared to, for example, optical frequencies. The next aspect at the bottom left is quite a challenging one, which says that we cannot simply amplify our quantum signal in a classical manner without losing our quantum correlations. On the one hand, this seems to be in quite good accordance with our first requirement of low signal level, but of course we have to keep in mind that what we want to be better at is the signal-to-noise ratio, and the reference system there is a classical system. And in classical systems, a quite straightforward approach to increase SNR is to simply crank up the signal power. And the fact that the quantum advantage is now only given for a very similar signal level compared to the classical reference, in combination with the inability to amplify the quantum signal, is of course already quite some disadvantage here. What we have to face next is the so-called delay line, or the quantum memory. As pointed out earlier, the idler, including all its quantum properties, need to be preserved until the signal is returned from the object to detect. And in principle, there are some approaches and some ways to do that, for example, by employing these quantum memories. Yet, of course, compared to a classical radar, this is another technological hurdle to overcome. What we have to do in order to create the signal that we send out is entanglement generation, and to directly generate microwave entanglement, we have to go down to very low temperatures. We are talking about something near absolute zero, on the order of 50 millikelvin, which is basically governed by the low photon energy compared to the effective temperature of our electron bath. Last but not least, the detector itself is also highly non-trivial, because with classical detection schemes, our potential advantage gets immediately lost. In sum, you already see it seems like a lot of challenges for a 6 dB improvement. But let's see. So far I mainly talked about some concepts, some schematics, and some theory, but what is the TR L, so what is the technology readiness level? We are talking about fundamental research, and the state we're in is really lab scale proof of principle experiments. This means that for now we squeeze the whole scheme, which you can see on the left, into some cryostat where we have the required low temperatures for signal generation and also full control of all system parameters, which means that not only signal generator and detector are located inside the fridge, but also some components model our environment as well as an object. Also, the path length is something we can now design to be perfectly the same, which means that for now we can skip the quantum memory at this stage. In the remaining time, I would like to give some insights into the actual physics behind entanglement generation of quantum microwaves and the signal detection, so the joint measurement which we intend to perform. What actually are quantum microwaves? How do we generate them and how do we control them? For quantum microwave generation, what we do is we work with superconducting circuits. And in such a circuit, we now design a resonator structure with a resonance frequency omega r, here illustrated on the top left, which is in our case on the order of several gigahertz. And this we can tune via some flux tunable nonlinear inductance to now control the resonance frequency. You can see the schematic of such a device on the top right, a so-called Josephson parametric amplifier, which is a two-port reflection type device which enables squeezing of electromagnetic waves via frequency down conversion and three-wave mixing. What exactly is now squeezing of light of electromagnetic waves? Well, let's have a very brief look at the phase-space representation of waves. As you can see there on the right, for continuous variables, you can either describe a wave with its amplitude for a given frequency and a phase, or you can decompose the very same wave into a sine and a cosine component with a respective amplitude Q and P. A classical noiseless signal now in this phase-space representation reduces to a well-characterized point in this phase space. If we now look at the quantum description of this phase space, we have to take into account the vacuum fluctuations, which are always present, and give a lower bound now on the phase uncertainty that we have. And this is nothing but another representation of Heisenberg uncertainty, which is nicely illustrated here. If we send such a vacuum state into a JPA, we can now literally squeeze the state in phase space to locally break the Heisenberg uncertainty on the cost of amplification of the orthogonal quadrature accordingly with some gain. You might wonder now, what do we do this for? Well, exactly these squeeze states are our quantum resource for the generation of entanglement. How I try to illustrate it here on this slide. If we create two squeeze states, illustrated by JPA 1 and 2 in blue and red, with the same squeezing level, but some orthogonal orientation in phase space, illustrated by the small blue and red box, and then we superimpose them in some microwave beam splitter, what we get out at the two output ports of the beam splitter is a pair of entangled modes. And these modes now locally entirely look like thermal states, which you can see here and there. So this is the local phase-space representation of mode 1 and mode 2. So locally, they seem to not have any quantum properties, but at the same time, which is quite interesting, is that these modes now show strong correlations between non-local quadratures, which means that, for example, the Q quadrature of mode 1 is highly correlated now to the Q quadrature of mode 2. Yes, this, to make it short, is the entanglement we work with, and we try to now make use of these quantum correlations in order to increase our SNR in the radar. Thus, what we send out in our radar is this mode, for example, could be the signal mode, and this is the mode which we store locally. Some central questions now are the following. How does the signal mode which we send out evolve locally when propagating through environment and also when hitting a target? And even more important, how do the non-local correlations between the mode evolve? Here it is fundamental to highlight that entanglement itself is also mathematically defined in such a way that it's extremely fragile and gets lost for sure when hitting any sort of target. At the same time, something which helps us at that point is that entanglement is only one of many quantum correlations which the signal carries, and some of the other quantum correlations are much more robust and persist the journey itself and also reflecting the target. Something I also wanted to highlight here on the right, where is it? Yeah. Is basically that entanglement per se is so weak in general that even the propagation path itself before hitting a target can lead to destruction of entanglement per se. Now let's say we rely on these remaining quantum correlations, and how can we now harvest these? How can we turn these to an observable quantity in measurement? Well, one thing is that the return signal and idler need to interact in a very specific manner, and the next thing is that we want to turn now these remaining correlations into such an observable such as the photon number. How do we do that? This brings us to the so-called joint quantum measurement. On the top, I try to highlight a bit how it works in principle. What we have is a returned signal mode and the stored idler mode, these two, which enter a mixer. I won't go into any details here, but the point of it is some specific interference between the two modes. And then we analyze one output of the mixer via a microwave single photon detector, which is basically built up by different resonators, some Josephson converter, and also transmon qubit. The current layout, the design of the mixer, of the single photon detector is highlighted here in the middle. We can nicely see the two coupling ports for the signal here on the left and the readout on the right, the different meander-like resonator structures. This is the Josephson converter, and here you can see the transmon qubit. Maybe you already suspect that this kind of configuration with transmon qubits at superconducting circuits just in a very straightforward way now requires these cold temperatures. If we now think a bit, what have we in principle done so far? Well, we now have turned ideally some remaining quantum correlations from a returned signal mode into a photon number, and from there on it boils down to a very classical decision theory, where we have some probability density distribution for different hypotheses. So there could be a hypothesis H0 illustrated in blue, and another probability distribution H1 for a target being present, illustrated in red, and then the overall error probability of the scheme for a chosen decision approach is then the sum of the false alarm probability and some misprobability. The detection probability is highlighted there via this red area. On the right, you can now see what is predicted by theory, where we have on the y-axis now the error probability exponent, and on the x-axis the number of copies of the signal that we send out, where with the gray dashed line we have an illustration of the classical limit, which is ideally achievable with a corresponding signal. In blue, we have the, I called it quantum optimal, so the 6 dB advantage we can theoretically achieve. And in red is the curve we are trying now to achieve and lab with the setup I just showed on the last slide with this microwave single photon detector. What is important now also to keep a bit in mind what has been achieved so far by other research groups, and this is highlighted there on the table at the bottom. And it is important to highlight that for microwave frequencies, this quantum advantage has not been realized. In any case, there have been some attempts, but always the proper experimental settings were not given. The only experiment which showed a very slight quantum advantage of 0.8 dB was realized for optical frequencies. And this is basically what we are working on now. We are trying to realize such a proof of principle lab scale experiment for quantum radar at microwave frequencies. And together with our newly acquired daughter company of Zurich Instruments, we have quite nice infrastructure in terms of technological solutions in the test and measurement area, where we together with these instruments and then the Rohde and Schwarz expertise try to fulfill this task. With that, I would like to conclude my presentation and some key messages I highlighted there on the left, which is saying that this 6 dB advantage I was talking about, keep in mind, it's given only for very specific working conditions, so low signal levels, and we cannot simply amplify these signal levels. There are now some discussions to find possible applications for this technology, but of course, even if we find some suitable applications, the complexity of implementation is quite large. So at the same time, there's no need to be too optimistic in terms of applications. At the same time, it is interesting because the field of research is quite active, and already this year there have been quite some interesting proposals. One I picked out there on the right, proposed by Jeffrey Shapiro, who's one of the most prominent experts in the field. And what he now is doing is diving into some more sophisticated applications where we actually do not rely on the 6 dB advantage itself, but we use the 6 dB advantage in quantum pulse compression to increase the range delay accuracy of a radar. And now we're not talking about a factor of 4, but what he's proposing is an accuracy boost of 28 dB to 8 dB. So this is some advantage, but it gets interesting also regarding some larger technological effort which may come along. Yeah, so let's see how that evolves. As you see, it's still a rather young field of research, but at the same time quite active. Thank you very much.
Anybody have any questions?
When do you think the quantum radar will take a step into production and actually be fielded?
Yeah, so the question was when the quantum radar actually will go towards production, if I understood it correctly. Yeah, that is a good question. I mean, as you have seen, it's really low TRL level. And then also the perspective for now is, I mean, if you talk to application engineers, they'd be like, why would I invest so much into something which yields so little? Yeah. At the same time, as I showed there at the very last slide, is that we just need a very good motivation in order to now take this technological complexity and having a good motivation for that. So there we still have to rely on some theoretical proposals, because for now let's say the promise is just it's not good enough. Yeah, I would say.
Thank you.
Mm-hmm.
Anybody else? Thank you. Oh,
Thank you very much for this very pragmatic presentation. It is really actually refreshing to see. Can I ask you, do you have a rough feel as to what photon number I need for a reliable detection? I remember in the early papers it was 1 photon per detection, then it became 100, then 1,000. Is there now a very rough estimate that you have as to how to link photon number to reliable detection?
How to link photon number to?
How many photons?
In the signal, you mean? Well, the point is, if you have too many photons in the signal, this is also something you can sort of imagine intuitively, is that very soon then you enter the classical regime. Yeah? And when they talk about low photon numbers, what they actually say is per mode, it's below 1 photon. Yeah? So there it's really, really low levels. And then it's a bit hard to wrap your mind around that if you think about it. But this is more or less the very restricted parameter regime. Yeah, so we're talking about something like 0.2, 0.3 photons per mode that we try to send out there. Yeah.
Thank you very much.
You're welcome.